I was just saying in the previous video that we're going to go ahead and work through these to see whether the sign of the entropy change is positive or negative. So I'm going to do the first one. And here we start with a solid, and it's decomposing to create another solid and a gas. And you might recall that if we have gas always has way more entropy than a solid. So that means there's much more entropy in the products. So the entropy change in that case is positive. Now I'd like you to pause the video and go through and try to predict the sign of the entropy change for each of these reactions. Okay, so now that you've tried that, I'm just going to run through these really quick. So in this reaction, the second one, we have 2 moles of one gas and another mole of another gas on the reactant side, and on the product side we have 2 moles of only one type of gas. There's much more entropy in the reactants because we have 2 different gases, so there's a lot more possibilities for the way things can be arranged than if we just have one type of gas molecule. And there's 3 total moles of gas, whereas there's only 2 moles here. So this one represents a negative change in entropy. Here we have something going from being a liquid to a gas, and when we go from a liquid to a gas, that automatically is an increase in entropy because we know a gas possesses more entropy than a liquid. For the fourth one, we have some dissolved ions that then form a precipitate. Dissolved ions possess more entropy than a solid, so this is a decrease in entropy. Here we have 2 moles of a gas combining to form 1 mole of a gas, so there will be more entropy on the reactant side simply because we have more particles. So this is a negative change in entropy. In number 6, we have a gas, we have dissolved ions as reactants, and in the products we have dissolved ions but no gas. So this will be a decrease in entropy. Gas always has more entropy. And in the final one, we have 2 different types of gas combining into one type of gas. So this will also be a decrease in entropy because there's more order when we only have one type of gas particle. So if we need to calculate the delta S for reaction, we're going to do something that's very similar to when we did heats of formation. Excuse me. So we're going to use this formula right here, where we add up all the what we call absolute entropies of the products and subtract all the absolute entropies of the reactants. We can find values for absolute entropy in the data booklet. They're in an appendix of Zumdahl. Sometimes they're given in the problem. But it's really, as long as you know how to use the numbers, it's not like you have to find them anywhere. They're just listed for you. So remember, when you're doing any kind of problem, especially on a quiz or test, that it's always a good idea to write the formula first. So you should write this formula out, and then below that do the work. So I need to add up all the entropies of my products, and I'm going to multiply by the number of moles in the equation. So the products in this case there are 2 moles of ammonia, and the ammonia has an entropy of 193 joules per Kelvin. I'm omitting the mole here because I've multiplied it by the number of moles in the equation, so that would cancel. So that's all of my products. Now I need to subtract my reactant. So I have 1 mole of nitrogen, and it has an entropy of 191 joules per Kelvin. And my other reactant is I have 3 moles of hydrogen, which has an entropy of 131 joules per Kelvin. So then when I calculate all of that out, I should discover that I have an entropy change of negative 198 joules per Kelvin. So negative entropy change makes sense. I have 2 different types of gas particles on the reactant side, and only one type and fewer moles of gas particles on the product side. So the products possess less entropy, so it's a negative change. What I do want to point out to you is that all of the calculations we've been doing in thermo have been in kilojoules, and entropy is usually given in joules since the values are much smaller. So that's going to be important when we come up to the next part of things in spontaneity, so keep an eye on that. So when we talk about spontaneity, we mean something that's going to happen without any outside force, any outside intervention to make it happen. And every process has a spontaneous direction. So for example, balls always roll downhills. They don't roll up by themselves. Iron will rust. It doesn't unrust. Okay? So when we talk about spontaneity, we're talking about in what direction does it happen without anything happening to make that happen. So we have this concept of Gibbs free energy, delta G, and it basically means how much energy is in a system that could do work. And for our purposes, it's really just a calculated quantity that allows the prediction of spontaneity. So Gibbs free energy, as I was saying, sorry, I got bumpy there for a minute, it's a calculated quantity. We're going to use it to decide if a process is spontaneous in a certain direction. This is the formula that we're going to often use to calculate delta G. It's in the data booklet. It's in table 1, and this is just a little blown up part to show you that it's in there. So it's not something you have to memorize, although I have seen it asked about on paper 1 when you don't have a data booklet, so it is a good idea to know it. But I think once you've used it 2 or 3 times, it pretty much sticks with you. So let's just look real quick at how we might apply this concept of delta G in different situations of delta H and delta S. So in this table, we're going to look at 4 different situations. So if we have a situation where delta H is positive, which would be endothermic, and delta S is also positive, what would the value of delta G be? Would it be negative? Would it be positive? And what does that have to do with the spontaneity? So if we look back at this formula that we've been given, if delta H is positive and delta S is positive, would we get a positive or a negative value? Well, it's going to depend on what the temperature is, which is what T stands for there. And then how does that translate into spontaneity? Well, the definition of delta G is if delta G is negative, then the process is spontaneous. So if this situation depends on temperature and it needs to be negative for the delta G needs to be negative for it to be spontaneous, then this term here needs to be large compared to delta H. This temperature is going to be, when we have high temperatures high enough to make this larger than delta H, then delta G will be negative and it will be spontaneous. So these particular situations will be spontaneous at high temperatures. If we have something that's endothermic and has a negative delta S, then let's take a look at what that would mean. Well, we've got positive here, and then a negative times a negative, so this is always going to be negative, then that basically means we're going to have positive plus positive, since a negative minus a negative is positive. So it's always going to be positive, so that means these will always be non-spontaneous. If you have something with that is endothermic and requires a decrease in entropy, it's not going to happen. Okay? If I have something that's exothermic and the delta S is positive, then let's look at what would happen in that case. So we have a negative here and a positive here. So a negative minus positive stuff will just make it more negative. So it's always going to be negative. That means these will always be spontaneous. Okay, which kind of makes sense, right? Something that gives off energy and also it has an increase in entropy. Both of those things would, it seems logical, would lead to something being spontaneous. If we have something that's exothermic and has a negative delta S, then again, this is going to depend on temperature, whether it's positive or negative. sorry, I'm a little trouble with my pen there. And in this case, it's going to be, if this is negative, and then this is negative as well, if this term becomes too large, then delta G would become positive. So these processes will be spontaneous at low temperatures. Okay? So this thing right here, the fact that delta G has to be negative to be spontaneous is going to be the key to this whole thing. So make sure you've written that down. So I just want to look at a couple of examples related to this that you might see on a quiz or on an IB exam. This is a question for an old IB exam. So which of the following combinations of enthalpy change and entropy change ensures that the position of the equilibrium will favor the products under all conditions? So if it's favoring the products, that means that the reaction is going in the forward direction. It's spontaneous. That's what this question is asking. So in what cases will it always be spontaneous? And from what we just saw in the table we just made, things that are always spontaneous have negative delta H's and positive delta S's. So if we then go here, we would need a negative delta H and a positive delta S. So C is the correct answer. All right, now we want to look at one where we actually have to do the calculation. So in this question, we're given a delta H, we're given a delta S, okay, so here, and we're given a temperature. So here's the temperature, here's the delta S, and here's the delta H. So when we put that in, the delta H is 124 kilojoules, the temperature is 298 Kelvin, and be careful, if we need our answer in kilojoules, then our entropy needs to be in kilojoules as well. So I need to convert that to kilojoules, divide by 1,000. And the answer I get for that is about 98. And I apologize, there's something went wacky with the answers for the multiple choice, but the important part is to see how you calculate this.